Here we discuss the incompressibility condition. Alright, so we will say that a flow is incompressible when the density of a material element is constant. So this is the definition of an incompressible flow, and of course mathematically one way of expressing that using the material derivative is simply to say that the material derivative of the density rho is equal to 0. This here condition is sometimes referred to the incompressibility condition. Note that this is the definition of an incompressible flow, and a flow is determined of course by the pressure field, the velocity field, and the density, but the incompressibility, so incompressibility here, the flow is incompressible, does not refer to the material property of the fluid. But of course, one particular cases of incompressible flows is when the fluid itself is incompressible. When the fluid is incompressible, and that means that the density is a constant, then the flow is incompressible. Okay, now, so this is one way of writing the incompressibility condition, but of course we have derived the continuity equation. Let me remind you, the continuity equation, which is mass conservation at the differential level, states that the material derivative of the density plus rho times the divergence of the velocity field is equal to 0, and therefore if the material derivative of the density is equal to 0, then in particular from mass conservation a direct consequence is also that the divergence has to be equal to 0. So note that because of the continuity equation, because of mass conservation, this statement here, this statement is equivalent to this statement. So sometimes you can use the divergence of u, actually in IF day, usually I would refer to the divergence of u being equal to 0 as the incompressibility condition, but I will also refer to it as the continuity equation for an incompressible flow. And this particular form of the continuity equation is the one that we will use in IFD, because in IFD we will really focus on incompressible flows.